Okay, so while we're waiting for everyone to arrive, can I just remind you, you have an assignment due 5 o'clock on Friday. If you need help on that, there is a couple of things available. First of all, computer help, etc. We have EMG 13 from 10 o'clock to 11 o'clock every Monday. Please feel free to come along to that. A couple of you have already, which is really good. I'm there from 10:30 onwards. So you can help one another and then get help from me. If you still need computer help or help with any assignments, don't forget to get on the Slack group and ask me questions, that's fine. I'll answer them, or the people might answer them. If you don't feel happy getting on Slack, remember you can directly message me in Slack, so it's not as if everyone has to know. You can always email me. At this point, I don't have a standard consulting session on Monday. If people think that we really need a consulting session, I can book an hour on Thursday. People think, are everyone pretty happy with the assignments at the moment? Or do you need an extra consulting session?
No.
Take it that you're all pretty happy, so we'll leave it as is. So, assignment due on Friday, computer help on Monday mornings, or Slack me, or email me, etc., or drop by my office. That's the main thing. So, let's recap where we go. Last week we started classification. Well, we talked about various classification techniques, but one of the common ways that people visualize how good their classification is a thing called ROC, or we say receiver operator characteristic. So you have a thing called an ROC curve. So let me just recap. The whole idea, and this paper should be in your reading list. This is probably my go-to reference for ROC curves. I still think it's really good, and it does more advanced stuff than we're doing in this course. So the whole idea is you start with a confusion matrix, and the idea of a confusion matrix would be that you have the truth, which is the favourite pet of these people, you have their predicted pet, and you want to see how these correspond. So here is your thing, and the classic thing is the rows represent prediction, and the columns represent the truth. And what we'd like ideally is to have lots and lots of positive numbers along the diagonal and zeros elsewhere. Everything that's not zero off the diagonal means you got it wrong. So, often we just look at the case where we have predicted false, true, false, true, false. And this is often referred to as a confusion matrix. So here's the standard form you will see. So you've got a 2 by 2 matrix. The rows correspond to predicted, and you've got a positive prediction and negative prediction. And then when you look at your columns, these are the true value, and you've got a positive condition and a negative condition. And there's 4 measurements we care about. The ones we really would like to be high are true positives and true negatives. And the ones we would like to be low are our false positives and our false negatives. Okay? Now there's lots and lots of ways of taking these 4 numbers and summarize them. And different disciplines have different ways of doing it. So, here's the first one. How about that side by side? Hey? How awesome's that? Guess what I spent my weekend doing? I have no fucking life whatsoever. The rest of you all, sex, drugs, rock and roll. Me, I got columns in Beamer. Well, I got columns in my markdown which told Beamer. So sensitivity. Sensitivity, specificity, mainly in medical fields. This is the classic one they do. So the first one, sensitivity, says if you look at TP and FN, so all the ones that are positive, what proportion of them do you get right? Specificity. Basically, of all the ones that are truly negative, what proportion do you get right? This is the standard one you see in machine learning. False positive rate. So false positive rate, now we take FP and TN. So all the ones that are negative, what proportion are they false positives? Well, true positive rate is, again, your true positive, your false negative. All the ones that are positive, how many did you actually get right? So you're looking at all the positive results and say, how many are right and how many are wrong. Precision recall. This is what the machine learners who are computer scientists use. So you'll see that often the mathematical machine learners use TPR and FPR. The precision recall is mainly for the computer scientists. So here, precision is you've got your true positives, your false positives. So these are all the ones that you said you predicted were positive. How many of them were right? That's your precision. Well, your recall is now your conditioning on this first row. All the ones that are truly positive, how many were actually correct? And obviously you can flick between them. The only reason I even had this slide is because I did some beautiful curves for a paper, and the reviewer said, but I don't understand your fancy curves. Can you do precision recall curves? Fuck off. Accuracy. This is saying basically, out of all these numbers, how many were right? How many did you say were positive when they were truly positive, and how many were negative when you said they were truly negative? There is more than these. There is also the F1 score, which is the harmonic mean of precision and sensitivity. And seriously, go to the wiki page and look at Fusion Matrices. There are pages and pages of different versions of these, I'm afraid. And different, you have to get to know them all, because depending on the person you go to, they have their standard. But how could we use this? Well, remember right back to the default. We had some data where for each person we would observe if they defaulted on their loan or not. And we fitted logistic regression. And then what we do is we can go to this data now and you say, what does the model predict? But it's going to give us a probability for each individual of defaulting. So you've got what we call a soft classification. It's basically giving you a probability. But every one that we've looked at so far has been a hard classification. I want to know, did you default or not? So how do you convert a soft classification to a hard classification? Well, you can choose a cutoff point. So in this table, I chose my cutoff point to be any probability that is greater than 0.75, I'll say you default. Anything less, you don't. And then I can put that in. I can now take all my probabilities. I can convert that to a hard classification, default or not. And then I can compare that to the truth, and I can get my 2x2 confusion matrix. But you might say, well, why 0.75? 0.5 seems to do better. So you can do 0.5. And you get a different confusion matrix, because as I change the cutoff, I will now have more that I say default. And so the good thing is, as that goes down, I pick up more of the ones that I should do, but also I pick up more of the ones that I shouldn't. And you can go down again. And in fact, they have a way of representing this, and this is what is called the ROC curve. So there's two ways you can do this. First of all, you could take a whole range of cutoff points between 0 and 1. And for each one of them cutoff points, you could get that little confusion matrix. Of the confusion matrix, you could calculate your TPR and your FPR. And then you could plot. So each one of these would be a little dot representing one of them confusion matrices. In fact, what they do is they don't actually do that. They say we will only consider the probabilities that we've actually observed. So you just rank them and you go down and you just do an accounting argument of at each point, when I add a new one in my cutoff as I slowly lower it down, did I add in a mistake or did I add in a correct one to pick up? The whole idea of this is you basically, if your model is good, it should sort of basically go up towards 1 and then shoot across. If my prediction method is as good as just tossing a coin, you basically get a line that lies on the y equals x line. So you can actually use this to compare models. And also, because we know that the more this line goes up to the top left, the better it is, the other thing you do is you can integrate that numerically, a thing called the area under the curve measurement. So, here is the algorithm out of Fawcett for doing that method. The whole idea is that once you've got a sorted list, it should be just order n, where n is the length of the list. In your assignment this week, I would like to attempt to implement that in R. So it actually works out quite nicely. So it follows through quite well. You just loop it through. You have to sort by your S scores, where your S scores is your probability type thing. So basically you started with the ones that are most likely to be a default, going all the way down to the least likely. You set up your FP and your TP to 0. You set up yourself a little blank variable for R. You set your Pugh's value to minus infinity, and then you limp through. And all you're doing is you're adding on a point, and each time you add on the point, you ask the simple question of, was it a true positive or a false positive? So you've got this cutoff, you're slowly going down the list, and every time you add a new observation, you just go, well, I've now said you're positive, were you a positive or not? Have a go. Well, not now, obviously. So, what I'm going to do is I'm going to actually compare. I've got 3 models, M1 up to M3. I can fit a general linear model. I've got family equals binomial, so we're doing logistic regression. Model 1 has both balance and income as predictors. Model 2 has just balance, and Model 3 has income. The response variable is default, with values yes or no. And here are my models. You can see that M1 and M2 are pretty similar. Very, very similar, in fact. And they're good prediction. Well, the blue line, M3, is not a very good predictor. It's pretty well, over the noise, it's lying on that y equals x. You could calculate your area under the curve. Here's the function that does it. Basically, you're doing trapezoid integration. Just counting through. You don't have to, if you do decide to implement AUC, do it all this way. You pretty well have all the data already in the first one. This does both getting the FPTP at the same time as calculating the area. And in our case, you can see that M1, M2, and M3 are all pretty good. M1's your best, slightly better than M2, but I would argue in this case, M2 is your best model, because it's nice and simple. So that's ROC. Now, somewhere I've got lecture 5. So now we're talking about LDA, linear discriminant analysis. So the first classification method we did was we recapped logistic regression. Now I have a look at another method, one that was invented by Fisher for the iris data that we've already discussed. So consider Bayes' theorem for classification. So our goal is to classify an observation into one of k classes. So let's assume that we have a prior probability that a randomly chosen observation is from class k, and we denote that by pi k. And also we have some sort of function, probability density function or probability max function, that basically relates the probability of observing our x, which is our predictor, given each individual class. And what we'd like to do is we'd like to use Bayes' theorem to obtain that. So what we'd really like to do is set up a model where I can go, okay, I've got my predictor x, given its value, what's the probability that y is class 1 or class 2 or class 3? So in our previous one, we'd like to go, what's the probability of you defaulting given your balance, or probability given your income? So here's our standard Bayes. The probability y equals k given x equals x is equal to the probability y equals k, which we use our prior, our pk, plus we want the probability that x equals x given y equals k, which is what we define there, it's our fk. Then we divide all that by the probability that x equals x. Well, that's what this is doing. This is using the law of total probability to get the probability that x equals x. So that's your standard Bayes rule. All good. So we're going to take this idea and we're going to look at it 4 times. We're going to look at it with LDA, then we're going to look at LDA with more predictors, then we're going to do QDA, and then we'll actually go and use it to do what we call a naive Bayes method. Okay, so we need, in this case, the distribution. We need to have that probability mass function or probability density function that relates our predictor with our response, our categorical response. So the first thing you can do, and we'll start with just a single predictor, p equals 1, to sort of get a feel for this. So we're going to assume that our fkx, so that's the probability density function that relates our predictors with each class, is going to be normal with a mean of mu k and a variance of sigma k squared. And initially we're going to assume that every individual group has the same variance. So it's like you look at it and you go, well, here's my normal distribution when k equals 1, and maybe my normal distribution when k equals 2, and my normal when k equals 3. So I've got these three normal distributions that give you information how this x varies for each individual class. Okay? And what we're going to do is we're going to take that and invert it and go, well, given I have my observation, can you tell me which of them classes it came through? And if I had a normal over here and a normal over here, it's really easy. If you observe something over here, you know I'm from this group. For all the people who are listening to this on the video, I'm really sorry, I'm just on the right side of the screen. I shouldn't have done the bean dance, should I, really? That was daft. I realise my mistake now. Well, the nice thing, if you do that, you can create this discriminant function. And how does this work? You've got delta kx, so you put in a value of x, and for each possible level, you do this calculation. You take x times the mu of k over sigma squared minus mu k squared over 2 sigma squared plus the log of pi k. So let's assume for a second I knew my mu k for each normal, I knew my variance, and I knew my prior probabilities. And what this is doing is it's looking at the relative probability of each of these groups. And so you're going, for this is the probability that I'm in group K given my observed data. So you've got this single discriminant function, you put in your value of x, and it spits out a number. And then the rule is you find which value of that, so for every class and for every observation, you will get a number. You choose the highest number, and that tells you for that observation which class you're at. Okay? That's your discriminant function. The problem is, I went, let's assume we have mu k, sigma k, pi k, which we don't. But we have a training data set. We're going to have some data we're going to use to train on this. And all we do is we know for our training data which class you're at. So you can calculate, you say, let's get all the training data that's from class 1. Let's work out the sample mean. Let's work out what proportion of data was in class 1. Go to the next one. All the class 2, work out their sample mean. And then finally what we do is we put all the data together and get an overall variance for all of them. So here's the actual calculations. We are going to estimate mu k by working out the sample mean of all the values of xi in the kth class. Let's go to the last one. We're going to get our estimate of the prior proportion by counting how many are in each class compared with the total. And then the middle one, all we're doing there is we're doing a pooled variance. We take every observation, take off its individual sample mean of the class it's in, square them all, add them all up, and divide by n minus k, where n is the number of observations and k is the number of groups. So let's go to our iris data. So let's remember how the iris data works. We have a load of flowers, irises, and we know for each one the sepal length, width, petal length, width, and species. And what we'd like to do is we'd like to predict species. And then we're going to have a single predictor at this point. So I'm going to choose as my single predictor sepal length. So what I've got here is a very rough, there's not a lot of data, but here's my little histogram. And what you hopefully see when you look at that is, if your sepal length is over towards the smaller values, about 5, you're more likely, if you look at that where all the pinky red in there, to be setosa. In the middle, you've got more the versicolor, the green ones, and then finally, as you get to larger values of sepal length, you get to a lot more blue bars, which is Virginica. So for example, if I came along and went, I have a flower, I know its sepal length is 8, hopefully looking at that, you instantly start to think you're more likely to be in the blue group. The same over towards the left. If I had something that's about 4, you'll be thinking you're in the red group. And to be honest, all that calculation is doing is, if I'm sort of about 5.5, it's looking at the relative height of each of them distributions to try and work out which is the better one to be. So here's my implementation. You should be starting to get used to my R by now, but let's just have a recap. So we set up a function. It's going to take x, y, x0. So x and y will be my training data. x0 is my predicted point. I've put a little verbose thing in there, so I can switch on a verbose, which will give me extra printout if I want it or not. I've defaulted to false, so it just spits out the answer, but I can switch on verbose to true, and it will give me an extra bit of information. So we're going to get our estimates first of all. So I count how many I've got, n, and I count k, the number of classes, and then I set myself up a little data frame. And what I do is I group by each class, and I get the mean and the pi. So all I've done there is I said, go and get my data, go and grab everything that's class 1, class 2, class 3, and for them calculate the sample mean and the proportion of the data that was in that group. Next thing is I quickly calculate my variance term. The next one is a little bit cheeky. What I did is I took my data frame, slice, will go to the first class and just grab the first row. And then the next thing I did is I then went, get me the column that's named mu. So it just goes to every class and it just gets the first row. Because I've used mutate, everyone in class 1 will all have a column saying the mean, sample mean, etc. So I've just used that to grab it. Now delta. This calculation there is directly off the previous slide. I've gone to, for each class of x0, I calculate the value. And I'm actually going to return all of them. I don't actually return the large, I return all of them so I can have a look. Then all my verbose does is it spits out all the internal data for me if I want to have a look at it. It just says we have to break it open. So here is my version. I give it sepal length. I give it Irish species. I say predict for 5, verbose equals true. And you see it spits out mu, pi, S2, and my delta. And you see the first one, 46, is the largest, which is a setosa. So I was excited about that when I coded up. Thought it was a nice little bit of leak code. Very excited. Does it work? First time it didn't, but the second time I got it to work. So how do you actually do it in R? Because you're not going to implement it yourself. You just do that to sort of get a sense of it. But there's actually an LDA built in, and it looks very similar to your standard linear models. Your LDA, you typical the LDA function. Your thing to the left of the tilde is going to be your response variable, which in this case is what class you're in, so it's species. The thing to the right is going to be your predictor. We have a single predictor, the sepal.length, and you tell it where the data is. Then I wanted to predict for new ones, so I said predict, I gave it the LDA, and I had to give it some new data, so in this case, a new little data frame with the sepal length equals 5, and it spits out, and it says the class is setosa, which agreed with ours. It's got the posterior probabilities. It actually takes that discriminant analysis and converts it to a posterior probability. I didn't bother doing that with mine. It also has the LD1, which I have no fucking idea what it is. As much as I looked at it, I couldn't work it out. So we'll just keep moving, pretend that we all know what it is. If anyone asks you, you just go look it up, and we'll pretend it's not there. It'd be best for all of us, won't it? So then I thought, is mine any good? So I tried. I went, fine, here's my prediction. I'm going to take iris sepal length. We're going to use our map function. So for every single one of them observations, it's going to fit me an LDA, where the training data is iris sepal length and iris species, and the value I want to predict for is the value I've just passed it. So it just goes along, it's just running along that vector. The first one it goes, fit the model, predict, fit the model, predict. I then converted that, because remember, they will return 3 values. Your discriminant for setosa and the other 2. And I just said, which of those values is the max? Is it 1, 2, or 3? Which you did there. I then did LDA predict. This is much easier to do because it just went predict LDA and return the class, convert that to a number. And then I said, is the number I'm getting, the number they're getting the same? So setosa would be 1, etc. And it went, yes, they're identical. I will then never use my function again because it's rubbish. And the one built in will be so much better than mine. So that was for p equals 1. That's a single predictor. But we have so much more data. So let's build it up. So now let's keep that same system as before. But now, instead of a single predictor, I'm going to have a vector of predictors, x1 up to xp. So we've got xp predictors. And what we're going to assume now is before we said that x given y was normally with a mean of mu k and the same variance. Now I'm just going to do the multi-dimensional version of that. So I'm going to say, let's read what it says. It says the conditional distribution of my predictors x equals some observed x given y is in k. So your class is k is a normal distribution with a mean of mu k, but now it's a vector of means, and you've got a variance covariance matrix. So again, instead of having that nice like there's my normal, now if it's 2-dimensional space, you go, well there's my sort of my normal for the first class, and this might be my normal for the second class, and this, but the only thing I'm going to do though is notice that the sigma's all the same. So they're moving around, but they've all got the same sort of elliptical structure. They've got the same variance covariance structure. So we're assuming that nice structure. In that case, you can do the mathematics. And when I haven't gone through the mathematics in either of these, it's a thing for you, a little bit extra in your own time, because I know how you love that. But you can now get your discriminant function. We'll take a vector of predictors. And to some extent, you should look at that and see that it's pretty well the matrix equivalent of the previous equation. You've got x transpose sigma to the minus 1 mu k. So that's your mean term. Your second one is your mean squared term. And then you've got your log. So let's say, again, now you will put in vectors, but it will return a scalar. You would look at the value of each one, and you would assign the class of this. So you do this calculation for every class for the point you're trying to predict. And you would assign to the class that gives the largest value. And to do that, we're going to need an estimate of mu k, an estimate of sigma, and an estimate of the proportions. And you just do the matrix version of that. So, go to the class 1, get all the observations at class 1, work out the sample mean. Now, of course, if it's 2-dimensional, that's going to return a 2-dimensional vector with the mean of your first predictor and the mean of the second predictor. That second thing there is the way of getting your variance covariance matrix. You might automatically look at it and go, yeah, but you've got a vector transpose a vector, it reduces a scalar. Notice the t is on the second one. So you don't spit out a scalar with this, what you actually spit out is a n times n vector. Oh, am I getting that right? Yes. Oh no, you get a p times p because you've got p predictors, sorry. So you're going to get a p by p matrix, so it's equivalent to your variance covariance matrix. The nice thing is, it doesn't look that much different. To do it in R, you do the LDA function. You've got your species to the left of your tilde, that's the categorical field we're trying to predict. And now I've done the 2-dimensional space, so I've got sepal length and sepal width as my predictors. Here's your output from that. And what I've done here is I've considered the sort of space of, and I just did the values we've observed in the data set. So I've looked at a grid of values for the possible values of sepal length and the possible values of sepal width. And then what I've done is I've coloured each point in that grid by the predicted value. And now you can start to see why this is called a linear discriminant analysis. Because you find the boundaries between these 2 points. That is the point where the value for 2 classes was the same. That boundary ends up being straight lines. In n dimension, it would be hyperplanes. So you can see your space there, and that will become even more when we get to QDA. QDA. It's almost like I wrote these slides. Although, to be honest, I have had, StatPrak 1, there's occasion where I go, and now we'll look at, oh, what the fuck is that slide? That's new to me. You forget. Or the worst, you walk out in front of a lecture theatre and you actually forget who the students are, and you have no fucking idea what you're meant to teach them. 300 engineers, and I walked out and went, who the fuck are you lot then? So we're going to release it a little bit. We've now got P predictors, but all the time we've been going, let's assume the variance is the same. Let's assume the variance covariance is the same. So before we had our class, it was like this ellipsoid, but it was the same and we were just shifting it around. Now we're going to have even more freedom. We're going to let for each individual class, it can have its own little mean and its own little variance covariance. Your ellipsoid can now shift around. You've got these circles, ellipsoids. So we're going to have our conditional distribution of x given y equals k is going to be normally distributed. It has its own little population mean vector, but it's also got its own little variance covariance term. What does that do? Well, first of all, you get some extra terms to take into account that before that assumption of equal variance covariance simplified your discriminant function. And we don't get that now, we get a bigger thing. You have to, the bits that we could cancel out before when we're comparing, you can't do as well. So you now get a bigger term. You notice that you've sort of still got your second term, the mu k, and you've got your mu k transpose, which is the equivalent of your mu squared term, but we've now got this extra xt transpose x that doesn't cancel out, and right at the end we've got the log of the determinant of our individual ones. The main difference in the calculations is still we can take each class, we can get the observations and calculate the mean, but we're going to calculate a variance covariance of each individual group. So instead of having this pooled variance covariance term, we have one for each individual one. How do you do it? There's a built-in QDA function. Very similar to before, now you do QDA as opposed to LDA. Your response variable species is on the left of the tilde, to the right of all the predictors, sepal length, sepal width, data equals I, spits it out, you can also do prediction.
What does the Q stand for?
Beautiful question. Quadratic.
We could guess that. Okay. Oh, I didn't read that.
Do not diss a good question like that.
It was on the previous
I will
slide.
take you outside and educate you.
It was on the previous slide, to be fair.
What?
It was on the previous slide, I didn't see it.
Yeah. But it is a really good question. What does it mean? It was called that because it was a quadratic. Because if you actually look at the discriminant analysis, there's now a quadratic term in there with that x transpose. And you can now see you get that curved form in the relationship. It was a good question. That was impressive. It's a chocolate frog sort of question.
Why are you having just let it go?
Pardon?
Where the triple frog?
Yeah, well, where's the lollies, John?
That's a good point. I should organise lollies for you, shouldn't I? I will be more compassionate and caring than bringing chocolate in. I know you're thinking, how could I be more compassionate, caring? I don't know. I will try my hardest because I've always been, oh, gentleman Jono, they used to call me. Oh, look at him, big softy. So LDA is an absolute classic. It's one of these things that I was never taught at all in my entire course. And when you go elsewhere, and they go, well, don't you just do LDA? And I go, I don't know what it is. Do be careful though. There is also another LDA, which is a latent Dirichlet allocation, which is actually a standard technique in topic modeling, which is a standard technique in natural language processing. So there is more than one LDA if you ever look it up, but the one we're doing is linear discriminant analysis. Okay, next one we're going to look at is naive Bayes. Unfortunately, naive Bayes is in neither of the textbooks. The two textbooks, Hasty and James, that we've been using, that remember is on the reading list, so you can have them freely available. Doesn't do naive Bayes, but this has come up quite a few times in some of the work I've done recently, so I thought it was a nice one to cover. So let's go back to this recap of Bayes. So what I'd really like to do is I've got some predictors, x, and I'd like to work out the probability that this observation is in class K, given those predictors. And Bayes' rule says, well, that can be written as the probability that x equals x given y equals k times the probability y equals k over the probability x equals x. That's Bayes' theorem. And you can think about it. Here we've got this, x equals x in bold. But actually, what I want is that joint distribution. I'd like the probability that y equals k and x1 equals x1, x2 equals x2, all the way up to xp equals xp. I'd like to get that joint distribution. Now I can write that as a series of recursive relationships where I can say, well actually I can rewrite that as the probability that x1 equals x1 given all the other predictors on y equals k. And then I go to the next one, I go times the probability that x2 equals 2 given all the predictors remaining and x equals k. All the way down to eventually I get xp equals p given y equals k times y equals k. So what I'm doing there is I'm taking that top term, which is the probability x equals x given y equals k times the probability y equals k. If you think about it, from the multiplication rule, it's equivalent to the probability y equals k and x equals x. And then put that in its long form, and then just broke it down to a load of conditionals. And here's the naive bit of naive Bayes. I make a very simple assumption now. I basically go, what if we made this idea that given the class, all my predictors are conditionally independent? All that means, if you look at any of these things where I go, the probability xi equals some value, given all the remaining and y equals k, I just go, I'm just going to lose all the x's in that predictor and just assume it's exactly the same as the probability xi equals xi given y equals k. In fact, I lied when I said that none of the two textbooks mention this. I went to look it up, and Hasty in his book went, something along the lines of, I think we know why it's called naive Bayes, because only a fool will use it. But people do use it, and you should know about it. Just going, I wouldn't do that, is daft. It's not bad. It works better than it should do. So it's really nice. All we need is for each individual class, the probability that xi equals xi. So you're just going to condition, you got rid of all this joint dependency and made that naive assumption. It is naive, but it works still quite well. All the predictors are conditionally independent given the class you're in. Because now, we can rewrite it. The probability y equals k over given x equals x, we've got a 1 over z. That z is just a huge normalization term. Just that's there to ensure that what I get is a probability. I basically sum over all of these and then divide by it. But it's the probability y equals k, so that's my prior probability, times the product of each probability that xi equals xi given y equals k. Now you can work out this probability by putting some sort of distribution on it. The most common one is they usually assume some sort of multinomial distribution, just do sort of case counting, which we'll talk about in a second. So we replaced that horrible big joint distribution by the product of a load of simpler ones, just on the assumption that given I know the class, I can just look at the product. Hence the naive and naive Bayes. So let's work through an example. So the data we've got here is House votes in '84. So this was the, I think it's like 430 members of the House of Representatives in America, and how they voted on altogether 16 votes. And there's actually 9 ways they could vote in the American system. These were classified into 3 levels. Basically, Yes, they voted for the individual proposal. No, they voted against it, or they abstained, which they've indicated as an NA. If you go and search the data, it actually explains all the classes, because you can vote for it, but you can also match up. So you can actually go and say, right, I'm going to vote for it, you're going to vote against it. We won't go to Parliament because they cancel one another. So they decided how to reclassify this. But what we've got here is we have our class, Republican or Democrat, and we have our votes. And you can see this vote, ignoring NAs, as a very simple Bernoulli. So I can start to calculate probability that vote 1 is a yes, given you're a Republican, by just going and doing some counting. We're treating it as a multinomial. I don't think I put there the package. The package you want to do naive Bayes, I believe, is the E1071 package. Is that the right name, Stephen? Yeah. There's a package called E1071. I don't actually know why it's called E1071. I assume it's like the room or the group they did, but it has a lot of machine learning packages in it, and it has a naive Bayes. So here's how I did my naive Bayes. So it's a naive Bayes command. I'm going to do class on everything else, but because I want it to be small enough to fill out the slide, I've just looked at the first 4 columns of my data, which is going to be the class and then the vote 1, vote 2, vote 3. So I just reduced down to them 3. And it spits this out. It has our prior probabilities of being a Democrat and Republican, and then our conditional probability. So for example, the first one says, given you're a Democrat, the probability that you voted yes is 0.60. And the probability you voted no on the first vote is 0.39. So in that term, I wanted the probability that x1 equals a value, given y, is that table. It's just assumed a very simple, in this case, Bernoulli distribution. And it's not doing anything more complicated than what you could do by hand. What I've done here is I've taken House votes, I counted the class, and then I used mutate to say, well, what proportion of my data are Democrats and what proportion are Republicans? 0.61, 0.38. That's how it got its priors. It just counted, said what proportion of all my data in the training data set are Republicans and Democrats. To do the other one, what I've done here is I've taken the House data and I've counted for each class what they voted for vote 1, and then got rid of the NAs, just trimmed it, grouped by class, added a proportion, and what you see now is this is how they get the numbers. They said for Democrats, what proportion voted N? 0.395. And so now to do any prediction, all you're going to do is you're going to take the probability of being a Democrat multiplied by the probability of whatever you voted from them table, and use that as your posterior prediction. Occasionally, you'll find they talk about a thing called Laplace smoothing. So sometimes you have no observed values for xi for a given class. In this case, we can add a pseudo count to each of the counts in the frequency table. So they found that sometimes when you have these cases where you're not observing data at that point, it's hard to separate. If you think about that probability, the probability that y equals k, let's go back to it. If you think about trying to work out the probability y equals k, imagine you have a particular xi, that for one particular class, no one actually had no successes. So there was a vote when no one voted for it. So in that class, if, for example, if the Democrats never voted yes for the first vote, that term there, when you do your thing, would be a 0. The problem is, you're doing a product and all the other numbers could be informative. You hit that 0 and bang, you get a 0. So you get these results that just sort of collapse down to 0 every single time. Because it just so happens that when you looked at one particular predictor, one particular class never had a particular level of that predictor. That sounded a hell of a lot more complicated than it really is. So let me see if I can illustrate with an example. So I made a false example here because I tried to find a real example and they were all nasty. So I thought I'll make a little false one. So here's my data set. I have a class. I have 4 observations from class A and 4 observations from class B. And there's 2 predictors, x1 and x2. And what hopefully you can notice is class B, on the first predictor, they only ever had n's in that particular one. So it makes it hard to predict. If I actually go and do my naive Bayes on this, you can see that when it comes to x1, B has 1s and 0s. And that 0 in that chart is going to make it hard to do prediction. Unfortunately for me, naive Bayes is clever enough to take that into account. So when I tried to break his prediction, it was doing some jiggery-pokery in the background to actually stop me doing it. But if you were doing this by hand, you would get to that point, you'd be trying to work out the probability that y equals k given your predictors, and you would be going times 0. And that would wipe it out. You can never get anything but a probability of 0. But what you could do, and the default thing you can see in the naive Bayes is it's doing a Laplace equals 0. It's not adjusting it. So let me just confirm what this is doing. I said let's do the grouping, and you can see you've got this probability of 0 and 1 on the case when you look at x1 for the class B. You'd be glad to know that the 4th line in my 1-line command, complete x1 fill equals this, blah, blah, blah. That's 20 minutes of my life I'm not going to get back. Because R tries its hardest to go, there's no observations there, why would you want that extra row in that table? And that final row 4 took a long time for me to persuade R that I really did want it. And complete's actually, now I know about it, is a good function. If you ever have data that's incomplete in a data frame, complete will help you fill it out. So now I did a Laplace equals 1. And suddenly we've got, if you look at that x1, which is our problem case, and you look at B, now the numbers are we don't have that 1, 0, which is going to cause us problems. We've got a 0.83 and a 0.16. It's been adjusted. And to see how it's adjusting it, here's me reproducing it. You do your group, you do your summarize, you do your complete, and then for every single observation, n, it's added 1 to them. So if we go back to the previous one, you can see n is 2240. And it's that 0. It's the case where you have class B and x1y, you have 0 observations. It's added 1 to all of them. So in this case, you end up with 3351. And also, your n is now 666. And it's adjusted those values. And that is it. So, Wednesday we have another lecture. Friday there is no lecture, no workshop, that's it. But you do have an assignment at 5 o'clock. Because we do have that lecture time on Fridays at 10 o'clock, I will be in my room from 10 to 11. So if anyone has any questions for the assignment, I'm happy to help you. Not that you need it, you're all sorted, but if you do have any last minute questions, please feel free to come and see me. I'll try and sit there. Other than that, I will see you all Wednesday. Thank you very much. Matt.